Hi there. My name is Ashish. I just graduated with a PhD in computer science from Georgia Tech. This work is a part of my PhD research, and it focuses on storage consumption behavior of apps on mobile devices. So let's get started. Smart mobile devices have evolved as versatile personal computing tools. There are millions of apps available for everyday needs, such as communication, gaming, entertainment, health, tracking, and home automation. Sometimes the device is used for work as well. So this versatility poses high storage demands. However, the storage capacity on these devices is limited. Most devices are not equipped with flash or SD card, while anecdotal evidence says that pictures and videos take up space. Modern apps are storage heavy as well. For example, this figure shows the maximum permissible app sizes by app stores over time. Um, the x-axis shows the timeline and y-axis represents size in megabytes. So as seen, the maximum app sizes have only been increasing. So today, a single app can consume up to 4 GB. Yet, no prior work has studied storage consumption behavior of mobile apps. This work presents the first ever detailed and large scale study on storage consumption behavior of mobile apps. We present three separate studies. First one is the longitudinal static analysis of millions of apps. Second is the install time consumption. And third is the post-installation or usage time behavior of apps. It's a user study that we carry out with 140 participants. Finally, based on our study findings, we propose a new storage management design and present preliminary evaluation. So let's look at the first study, which is the longitudinal study that analyzes millions of Android and iOS apps from 2014 to 2019. The research questions that we answer here are: how have the apps evolved over time, and what causes increase in app sizes? So let's look at our findings. The findings from a longitudinal study suggest that apps have been steadily growing in size over the years. This graph shows app size in log scale on x-axis and cumulative distribution on y-axis. We particularly found that almost 5% of Android apps in 2019 were at least 100 MB in size, compared to only 0.3% such apps in 2014. Why is that? This is because of the change in App Store submission policies that allowed developers to submit apps up to 100 MB in size. So that's why the developers have been creating bigger apps. And we find similar trend with iOS apps as well. Next, we compared the sizes of common apps across years and correlate that to app popularity. So in this graph, x-axis shows increase in app sizes, and y-axis shows the download range, and bars depict the size increase. So we found that popular apps grew more in size compared to other apps. This suggests that as apps become popular, that is, they receive high number of downloads, developers pack more functionality in the same app to engage and monetize users, creating super apps. A good example of super app is Uber. They recently added food delivery services to their ride-hailing services and expanded into markets beyond the US. This caused the app to grow bigger in size. And there are more such apps. So what causes apps to increase in size? Well, we found that the first reason the increase in size is because of more features. Developers pack more features. Uh, and we found that by analyzing millions of free Android APKs over the years. Uh, we showed this graph that compares number of features in Android apps from 2014 to 2019 on x-axis. Here we use Android activities as proxies for features. Since an activity offers a particular feature or allows users to perform a specific task, such as logging in or taking photo. However, we note that not all functionality or features are free. Apps do offer paid features, but those are only unlocked once the user pays, but they always consume space on the device. Second reason of app size increase is use of third-party Java SDKs. The graph shows number of SDKs on x-axis in log scale and cumulative distribution from 2014 to 2019 on y-axis. We found a whopping 800% increase in average number of Java libraries per app in 5 years. What are some examples of these SDKs? The table lists some of the examples. Particularly, we found that the number of apps using advertisement SDKs doubled in 5 years. Similarly, the number of apps using social media plugins almost tripled in 5 years. However, we found that since SDKs are generic, a large subset of functionality is unused. Moreover, users may only choose a certain type of functionality. For example, if there are multiple social media plugins available in an app, the user may only use their favorite. This leads to inefficient use of storage. The next reason we found for size increase was more native libs. We found that modern apps contain more third-party native libraries. Not only that, we found that developers develop one and use everywhere universal apps to reduce engineering effort. Such apps support multiple hardware architectures such as x86 MIPS in the same app. However, these redundant libraries are not used. For example, x86 native library will not be used on ARM device, but they unnecessarily consume storage space. We also found that apps from the same vendor contain same native libraries. For example, Facebook, Instagram app contain a few common libraries as both apps are from the same company. Moreover, third-party SDKs that implement common functionality across apps result in code duplication. For example, use of same version of Crashlytics SDK across apps to enable easy debugging. These common SDKs and native libraries lead to duplicate files, consuming more storage than necessary. The next study looks at install time, storage consumption behavior of apps. Specifically, we look for how much storage is consumed during app installation and what causes this consumption. To do so, we analyzed top 30 Android apps and measured their storage consumption. Our install time findings suggest that during installation, app APK is downloaded from the App Store, and the app is optimized for performance at the cost of more storage. This graph compares app download sizes versus app install size. Y-axis shows the size in megabytes. As seen from the graph, during installation, apps further expand to consume a significant chunk of storage space. This is because Java code is pre-compiled into native for best runtime performance, and libraries are unzipped for faster access. On average, we found that the app install size is at least 1.5 times of its download size. Next, we look at the usage time storage consumption of apps. Specifically, we look at how many apps typically users interact with daily and what fraction of apps and features are actively used. To do so, we conducted a user study with 140 participants across multiple age groups, gender, professions, recruited through PhoneLab testbed. Each participant was assigned a 16 GB Nexus 5 smartphone running Android. We built and deployed a context-aware storage tracing tool that collects not only file system events, but also user context such as apps users interact with, features that are being used, day of the week, time of the day, and others. Let's look at our usage time findings. This graph shows breakdown of storage consumption across 21 users. The x-axis shows users and y-axis shows size in megabytes. Contrary to common intuition, we found that average 50% of the device space is consumed by apps. And on average, each user has about 122 apps on their smartphones. However, we found that only 10% of apps and features are actively used. Next, we looked at storage consumed by various app components across same 21 users. We found that on average 20% of the storage is consumed by app caches. This suggests that app developers freely use persistent storage by caching content to improve runtime performance and offer streamlined user experience. We also found that developers or apps hoard data such as debug logs, they create user analytics, and they download video advertisements as needed. So let's summarize our findings and present a case for storage management on mobile devices. So a study shows that modern apps are feature-rich, monolithic packages. An app from 2019 packs twice more features and consumes twice more storage than an app from 2014. We believe that this trend will continue, particularly as the mobile technology evolves and richer and more immersive apps supporting augmented reality are introduced. We also found out that according to Counterpoint Research, the global storage capacity of smartphones sold in 2019 was 54 GB for Android and 134 GB for iPhone. This suggests that low-end devices, Android devices, are still prevalent. Although users can choose to pay a premium price for additional mobile storage, our findings suggest that modern apps are optimized for performance and not storage. For example, they contain more features, more SDKs, and native libraries. However, only 10% of features are actively used. Common SDKs and libraries across apps lead to duplication, and there is no deduplication currently on mobile devices. Furthermore, app developers freely cache and hoard data. There are no quota limits. This makes a case for an efficient storage management on these devices. So based on our findings, we propose an automated context-aware storage management of mobile devices, where we assert that the operating system must automatically reclaim space occupied by infrequently used apps and features. Moreover, we propose that multiple reclamation techniques could be used. For example, as opposed to compiling all Java code in apps. A content adaptation technique could be used to selectively compile Java code that is heavily used, that is actively used, saving on storage. Similarly, a common SDKs and libraries could be deduplicated. Libraries that are infrequently used could be kept in compressed form and could be decompressed on the fly, saving storage. Finally, caches of infrequently used apps could be deleted, yielding more savings. We present preliminary evaluation of our techniques using top 30 Android apps. The graph compare energy consumption, launch latency, and storage savings under various settings. The default settings is optimized for performance. That is, all Java code is pre-compiled to native for best performance, regardless of its use. Under quicken setting, only a few Java classes are compiled into native, yielding about 25 MB of storage savings per app at no storage, at no overhead. So there's almost negligible overhead in terms of battery and launch latency under quicken settings. However, when no Java code is pre-compiled, which is under no OAT setting, we see more storage savings. That is about 50 MB of storage savings per app, but that comes at the cost of high latency and battery. However, we believe that this high overhead is acceptable for infrequently used apps. Similarly, we found that a simple file level deduplication can save about 1 MB per app on average. These are just the preliminary results, and more research is needed. Thank you so much for attending the talk. Our storage tracing tool, which is Cosmos and study data, is publicly available at this GitHub website. And our user study data is available from PhoneLab website. Thank you.